Imagine peering across light years to analyze the atmosphere of a distant world, only to find nothing. That's the frustrating reality facing astronomers studying sub-Neptunes, exoplanets smaller than Neptune but larger than Earth. Instead of revealing the secrets of their formation, many of these planets present a frustratingly flat spectral signature, particularly in the near to mid-infrared wavelengths. What is causing this flat spectrum conundrum, and what does it mean for our understanding of these intriguing worlds? This puzzle, as detailed in a recent paper, astroph.ep, November 30, 2025, has spurred considerable debate. Transmission spectroscopy, a technique where scientists analyze starlight that has passed through a planet's atmosphere, should theoretically reveal the atmospheric composition. But for many sub-Neptunes, the data suggests a near-featureless spectrum, implying a lack of distinct chemical signatures. Initially, two leading explanations emerged: atmospheres dominated by heavy metals or the presence of pervasive, high-altitude gray aerosols, tiny particles that absorb light equally across a wide range of wavelengths. But here's where it gets controversial. Observations of escaping hydrogen and helium from these planets have largely ruled out the metal-rich atmosphere hypothesis. The lighter elements are escaping, suggesting an atmosphere primarily composed of hydrogen and helium. This leaves aerosols as the prime suspect, but not just any aerosols. Homogeneous distributions of small aerosol particles simply can't produce the observed flatness. You'd expect to see some wavelength-dependent scattering. On the other hand, larger particles could create a flatter spectrum, but they require incredibly high production rates that defy realistic atmospheric models. So, what's the solution? The researchers, James E. Owen and James Kirk, propose a compelling alternative: heterogeneous, or clumpy, aerosol distributions. Instead of a uniform haze, imagine pockets or clouds of aerosols concentrated in certain regions of the atmosphere. These clumps, even if only moderately optically thick, can effectively flatten the transmission spectrum even with smaller, more realistically produced particles. And this is the part most people miss. Clumping increases the effective mean free path of photons, the average distance a photon travels before interacting with a particle, while simultaneously reducing the wavelength dependence of the aerosol's interaction with light. This allows the aerosol distribution to act as a more efficient gray absorber, mimicking the effect of larger, more uniformly distributed particles. To test their theory, the team applied this framework to TOI 776c, a well-studied sub-Neptune exhibiting this flat spectrum phenomenon. Their models demonstrate that clumpy aerosols can indeed reconcile the observed spectrum with a primordial hydrogen/helium-dominated atmosphere, resolving the tension between the spectral data and the planet's likely composition. Furthermore, the authors explore the implications for emission spectra. A clumpy aerosol distribution will allow stellar radiation to penetrate deeper into the atmosphere and also alter scattering patterns. This could lead to observable signatures in the planet's emission spectrum, providing a potential avenue for future observations to confirm the presence of these clumps. Think of it like looking at clouds on Earth. Sometimes they're thin and wispy, other times they're dense and block the sun. The same principle applies to exoplanet atmospheres, but on a vastly different scale. The broader message is clear: we can't treat exoplanet atmospheres as perfectly homogeneous environments. Aerosol heterogeneity needs to be seriously considered when interpreting atmospheric data, especially with the advent of powerful telescopes like the James Webb Space Telescope, JWST. JWST's ability to probe exoplanet atmospheres in unprecedented detail makes understanding these complexities even more critical. This research also highlights the need for theoretical work to investigate the physical mechanisms that could generate these clumpy aerosol distributions in the first place. What processes are at play that cause aerosols to aggregate in this way? This research, accepted for publication in the monthly notices of the Royal Astronomical Society, MNRAS, offers a potential pathway to understanding the atmospheric mysteries of sub-Neptunes. But does it fully resolve the flat spectrum conundrum? Are clumpy aerosols the answer, or just an answer? Could other factors, such as undetected atmospheric layers or complex chemical reactions, also be contributing? How can we definitively confirm the presence of these clumps through future observations? Share your thoughts and alternative explanations in the comments below. This is a rapidly evolving field, and your insights could help shape our understanding of these fascinating exoplanets.